All right. Hello, everyone. I'm assuming you can see my screen and hear me well.
Yes.
All right. Thank you for having me virtually. It's very nice to be back here to give a seminar in Leuven, even if it's virtual. I think some 10 plus years since doing my master's thesis with Connie, and to be back here. So I want to talk today about the architecture of planets and their host stars. And what you're seeing here in this image is all the currently known transiting exoplanets. And so there is a few thousand of them. And then here in white, just in the center of the image, I'm showing you the solar system planets. So there's 8 of them. You can probably easily make out the 4 largest planets in our solar system, but there's also there's smaller dots there with all the planets in our solar system. And so the other planets are the exoplanets, and they're indicated to scale. So that's telling us clearly that a lot of these exoplanets are actually quite large. But more and more, we're also starting to find the smaller exoplanets, even the Earth-sized extrasolar planets. And so we are really at a point where we have a high number of these exoplanets, really hundreds or even thousands of systems now that we can study. And in this next 40 minutes or so, I will try to give a bit of an overview of like what can be learned from many of these exoplanets and from these exoplanet systems, as well as linking that to their host stars. So let's try to make this this nice image a bit more quantitative. And so this is a plot which shows semi-major axes, so distance between star and planet mass. And so if we put the solar system on there, these planets look like this. And so, of course, Earth there at 1 AU and 1 Earth mass. And so even without putting any exoplanets here, it's striking how different the solar system planets are among each other, because this is a log-log plot, and so they span orders of magnitude in both distance between from star to planet, as well as mass of those planets. And so they really are spanning this kind of wide range of diversity. If we overplot the exoplanets on this plot, sorry, I should probably say, maybe want to add Pluto here for some enthusiasts, they would even fall off this plot. So that would even increase the diversity. If we want to put the exoplanets on there, then things look something like this. And so now you're actually increasing the axes on this plot even further. You have planets much further out and much closer in than anything in our solar system. And you have planets with masses that we don't really see in our solar system, some very high masses, but also, for example, some here in between sort of Earth and Venus and Uranus and Neptune, where we don't have many analogs in the solar system either. The other striking thing probably is that even though we've been studying exoplanets now for a good 20 years, we haven't really found analogs for essentially anything in our solar system. So the bottom right of this diagram here is still very empty. And so we haven't really filled that, which is very predominantly an observational bias. It's still very hard to find planets that are both low mass and long period. And so we're just having a hard time finding these kind of planets, which is why we haven't really filled out the bottom right of this diagram. And that's made more clear perhaps if we color code this same plot by detection methods. And so these planets are detected by 4 main different methods with imaging. So that's directly imaged planets, where we filter out the starlight to just see the planets at giant planets at long periods. There's the micro-lensed ones here, kind of spanning a wide range of masses at sort of intermediate distances to their star. And then the 2 biggest contributors to points on this plot are the radial velocity method, where we're measuring movement of a star caused by a planet, and the transit method, where we're measuring change in brightness of a star due to a planet. And so transits and RVs are really contributing the most to the demographics as we know them today. So it's worth emphasizing, though, here that nearly everything we know of these planets is actually measured only by seeing their star. So the transit method, we don't actually see a planet transiting. We just see a change in brightness of a star. The RV method, we don't actually see the planet at all. We just see the movement, not of the planet, but only of the star. And so everything's indirect. And so host stars will turn out to be rather important to make sense of anything we're actually observing. So in this talk, I want to talk a little bit about architecture, about dynamics, about the type of planetary systems we can find. And so this is my cartoon of what the solar system looks like, with 8 planets orbiting the sun in the middle. that rotation of the sun is more or less aligned with the plane of the planets, and all these planets are more or less in the same plane. We sometimes call it a bit of a pancake model. Everything there is really in the same plane, and also these orbits are fairly circular. They're essentially all nearly circular orbits. And so I want to sort of address here questions about how that would look like for exoplanets and whether exoplanetary systems dynamically look similar to this picture or not. So let's again quantify that a little bit more first. So this is the solar system and their eccentricities. And so you have Earth at 1 Earth mass and a nearly circular eccentricity. So nearly circular orbit. So eccentricity 0 would be perfect circularity. And then Mercury at the lowest mass there at about eccentricity of 0.2. So that orbit's slightly elliptical, but still quite circular. Now, if you overplot the RV planets for which we have been able to measure eccentricities, then the picture looks rather strikingly different. And it looks something like this, with quite a few of these planets being very elliptical. So this is typically giant planets with very elliptical orbits, nothing like what we see in our solar system, even with a few eccentricities all the way up to 0.92 or so. So this picture might resemble more what you're used to from seeing this type of picture for binary stars than for what our solar system with its planets looks like. So the question here is why exactly that is the case, and also how special is our solar system then? And importantly, we don't really have a lot of data points on the left-hand side of this plot. And so we're, of course, also interested in trying to understand what about the smaller planets? Is this something that exclusively occurs for large planets? There's a bit of a hint there that if you go to lower masses, you actually have less of a range of eccentricities in this plot. And so we wanted to set out to actually fill that left-hand side of that diagram. But it turns out to be very hard to do this for low-mass planets. And that's because mostly we measure eccentricities through radial velocities, and that method is just very hard for these small planets. So let me show you how that works. So this is how the RV method works. I'm sure you're all familiar. So you're measuring this blue shifted light of a star and the red shifted light of a star over time, and that's caused by that planet orbiting around, but you don't actually see that planet. Now this is if the orbit's circular, this movement has the same velocity all the time because of Kepler's law. And because of the same velocity as a function of time, the radial motion will then look like a perfect sinusoidal motion. And so you can just measure that. If, on the other hand, the orbit's eccentric, then you get these regions where star and planet are close to each other. And when they are, they're moving faster. And so you get this kind of non-sinusoidal shape as a function of time for the radial velocity. So this is how we measure RVs. How we measure eccentricities from RVs. It's fairly straightforward as a principle, because you can take data points at any point in time, at any point in phase. And when you do so, you will reveal the shape of the orbit, the angle of periastron, and the eccentricity. And so you can just measure eccentricities there. Now, unfortunately, if you go to very small planets, then the amplitude of the RV signal here is just very small. And it becomes very hard to find these planets with RVs in the first place. And measure the eccentricities is even harder. So the most obvious way forward here will be to use transits instead. We've known for a while now that transits from satellites like Kepler and TESS provide us with smaller planets, lower mass planets than the RV method. So we can just do a little bit better there, and so we can find smaller planets in that way. But transits typically don't actually give us RV information, and so the eccentricity information. And the reason for that is that this is how a transit looks like. So you have you measure the brightness of a star over time. You see that drop in brightness as a planet crosses in front, and then you will return to the full 100% brightness after. So this works very well, and we can do this to great precision with space instruments, and that means we can find even very small planets. But you're losing that orbital information. You can only see the transit happening. The transit will last a few hours. But the whole orbit might be days, tens of days, or hundreds of days. And so until the next transit happens, you're essentially blind to where your planet is. You can't just map out the full face. You're only having this very small part of the transit that tells you when the planet's right there, but then you don't know what the shape of the orbit of the planet is at any other time. So there are some ways forward here, and the most obvious way forward here is to actually use the duration of this transit to derive information on the shape of the orbit. And so the basic concept is illustrated here. So if you have a very eccentric orbit, for example, then depending on where your transit happens on that orbit, you might have a very long or a very short transit. So for example, if your transit happens right when star and planet are close to each other, your planet's now going to be moving very fast. And so as it's moving very fast, the transit will not last very long. And so you have a very short transit. And oppositely, with the same eccentricity, but a different orientation, you can now have a very long transit because the planet might be moving very slowly right where the transit happens. So that's the idea of the method. It is if we can find some of these very short or very long transits, that will tell us some very elliptical orbits where sort of the regular duration transits are the circular orbits. Of course, to then do this in practice, you need to sort of have a calibration. You need to know what regular duration means and to then benchmark what long and short really means. And it turns out that that typical duration for a circular orbit is actually set by the density of the star. And that's not entirely intuitive. It may be intuitive to understand that the radius comes in because a bigger star takes longer to sort of pass in your transit. So of course, the different stellar radius, bigger star means longer transits typically. The mass also comes in, again, from Kepler's laws, where the total mass of the system will set the typical velocity of bodies in that system. And so it turns out in practice that it's the density of the star that regulates how long a transit lasts. And so what that means is if we know the density of the star, we can benchmark how long a transit should last, and then long transits relative to that benchmark are eccentric orbits, and short transits are as well. And so we can use this method, this transit duration method, to actually get at orbital eccentricities. And so here is something where understanding stars will become very important, because we will need to know stellar densities very precisely. And this is something where astrocosmology can come in to be sort of our tool of choice in exoplanet science, as it can clearly provide stellar densities to the greatest precision. And when I'm saying astrocosmology here, I am talking about solar-like oscillators on stars that are typically very similar to the sun, quite perhaps unlike the type of stars, type of hot stars probably that many of you are working on. But so of course, for solar-like oscillators, we understand oscillation patterns quite well. We can quite straightforwardly get delta nus and nu maxes. And so as a result, we can then use scaling relations or measure individual frequencies to get stellar densities out. And we can do that. It's the easiest parameter to get out. Typically, we can often do that to the percentage level, 1 or 2% precision on the star. And so if we do all that, if we use astrocosmology to get a very precise stellar density, if we then also measure transit durations very precisely, and both of these are actually not very straightforward at all, but I'm going to gloss over the methodology a little bit to show you the results. But if we do those two things, then we can get orbital eccentricities out. And so that's what we did. We took a sample of exoplanets from Kepler, where we were able to do astrocosmology and able to measure transits very precisely. And so as a result, we could then get some eccentricities out. And so here again is the same plot, showing only planets with periods over 5 days. Otherwise, you have tides that become too important to see anything. And so we then measured orbital eccentricities for some transiting planets, which were typically lower mass or lower estimated mass, because often these masses aren't actually known for sure. We know their radius. And so then we found their eccentricities, and they looked something like this. This is work I did during my PhD. And so what this plot's showing is that really most of these systems, the vast majority, if you just count the number of blue points here, are actually very circular. They actually have eccentricities often quite close to circularity. And keep in mind, of course, these data will never go below 0. So they're easily biased positively. Many of these are very close to circularity. There's a few up here that appear to have higher eccentricities, but if you would look at the underlying data, they're actually the data points with the highest error bars typically. And so suggestive that actually many points are consistent with circularity if you would measure them very carefully. And so it turns out these systems that we were looked at, which here were only multi-planet systems, Kepler systems with multiple small planets, were actually quite similar to our solar system with multiple planets, and so with lower eccentricities. And so this, at the time we interpreted it as saying, okay, if you have giant planets, they might behave like binary stars with highly elliptical orbits. But if you go to typical multi-planet systems with multiple small planets, then you're actually in the regime where things are not that different from the solar system anymore. Now, we then afterwards wanted to also look at single planet systems, so systems with a single transiting planet, which we had originally excluded because there were more concerns about some of these planets not being real than being false positives. But that got better over the years. And so a few years later, we kind of revisited this work to go at single systems, so one known planet. That doesn't mean there's only one planet, but one known planet. And we measured their eccentricity, and this is where these data points started falling. And at first glance, it actually looks relatively similar with a lot of kind of circular points here, but it's actually noticeable that there's fewer of these points down here, and there's quite a few more, relatively speaking, of these higher eccentric systems, including some with very clearly not consistent with circularity. And so we did kind of careful analysis, the kind of careful underlying analysis. We tried to estimate what is the likely distribution of eccentricities that could produce this type of individual measurements. And so we didn't just take the best values, we took the underlying posteriors that we all had for all these systems. And so we did this hierarchical Bayesian way of estimating an underlying distribution of eccentricities that could produce these data points. And when we did that, we actually found a pretty clear difference between these singles and these multis, with the typical distribution looking something like this. And so you see for the multis, there is a tail towards higher eccentricities, but it peaks very strongly with nearly circular orbits being the most likely. And the singles, on the other hand, you still have that peak, but there is a much longer tail towards having more systems with higher eccentricities. And so that was interesting. That suggests that there's some clear dynamical difference between these systems, and that, of course, begged the question as to why that was the case. And I think there is two kind of main theories that now potentially could explain this. And so you need to understand how you would get the eccentricities in the first place. And so one picture has to do with what's called self-excitation. That's where you have scattering between multiple small planets that can increase their eccentricity. But when it increases the eccentricity, it will typically also increase the inclination between planets. And so when you get higher eccentricities, you will then also get misaligned planets from each other. You will no longer be in the pancake as in the solar system. And so when you then look at those systems in transit surveys, they will appear to be single planet systems because other planets won't transit. And so if that's correct, that means that the single systems with higher eccentricities aren't really single. They are just multis, which are not in the pancake. And so as a result, they would appear to be single with higher eccentricities. Another theory has to do with outer planet perturbations. So here you're assuming that most of these planets that we're measuring, which are small planets at relatively short periods, are perturbed by outer Jupiter-like massive outer planets, which can influence the inner orbits and in some cases lead to eccentricities. And so most of these theories can explain how that would work, and they depend then on the initial conditions of the disk, the amount of gas, whether you get more scatterings or more mergers and so on, and that could provide a range of eccentricities, kind of the way we observe. And so just to show you, this actually seems to work, at least in a general sense. We looked at the outer planet perturbations in some detail. We looked at some simulations of how, what eccentricities could that produce. And we tried to compare those to our measured distributions here for this type of planets. And that's how things then look like, where you're seeing the simulations and the data. And indeed, there is a pretty clear, there's some evidence here that this indeed seems to be happening, that you expect this difference between the multis and the singles, kind of roughly, at least in the way that we're indeed observing it. So kind of encouraging that we're able to understand, I think, what's happening. But the problem remains that these two theories each make their own predictions, and it's very difficult to entirely separate between the two. So full understanding is still work in progress, but I think we have learned quite a bit here on eccentricities for planets. And so to summarize, that was my solar system picture. If we then look at exoplanets, we first saw that for giant exoplanets, for massive exoplanets, it turns out to be that they're often highly eccentric, but systems with small planets are generally more like the solar system, especially the multis. but there is also some that appear to be singles, which are quite different for reasons we are beginning to understand. So that was eccentricity. Now, very briefly, I want to just have a look at another part of this solar system dynamics picture, which is the stellar rotation. And so, as I said, for the solar system, we typically have an aligned orbit between the planets and the stars. So that means the sun rotates in such a way that the plane of that rotation is the same plane as the orbits of the planets. It's aligned. Now, if we look at exoplanets, that's not generally the case. And so we have found exoplanets that are quite misaligned from their rotation of the star. In fact, we have planets that seem to orbit over the poles of the star rather than sort of following the rotation of the star. We have even planets that orbit completely retrograde, their orbits being retrograde relative to the orientation of the star. Again, making you wonder how that could happen, of course, if all these planets form out of the same kind of rotating cloud of gas and that collapsed into a rotating disk. And so first question is how can we actually measure this angle that we call the obliquity? And in exoplanet science, the most common one, which again might be familiar with from binary stars, is making use of the Rossiter-McLaughlin effect. And so the Rossiter-McLaughlin effect is one where we do spectroscopic studies of a star during the transit of a planet. And so as that planet's crossing over a rotating star, that star, because it's rotating, will have blue shifted and red shifted light because of its rotation. And now that planet will be blocking alternatingly blue light or red light, depending on where it is. And so if you take these spectra of the star during the transit, you will kind of see which part of the light is being blocked at which time. And so you'll be able to map out the relative orientation of the orbit versus the rotation of the star. Now, that only really works for at least some giant planets. It's because if you go to very small planets, it's just there's not enough light being blocked. There's not enough blue light or red light that's being blocked. And so it's very difficult to do this for the smallest planets. We have started making some progress, but it remains very, very difficult. Nevertheless, though, the small planets are the ones we're interested in often, because it's easier to see how, for example, giant planets could have migrated, could have been kicked out of the system, could have become misaligned. But we would like to know, what about small planets, often multi-planet systems? Could they also have been misaligned, or are those typically more like our solar system? Are those going to be well behaved, so to say? Are they going to be nicely aligned or not? If they're not, we would need different explanations for how that could happen. And so here again, astrocosmology, and I'm again talking about astrocosmology of solar-like oscillators, can be a bit of a rescue because it can actually provide us stellar inclinations. And so that comes from rotational splitting of individual frequencies of oscillation. So where you can split an individual frequency into, for example, a triplet. And that splitting will tell you how fast the star is rotating, but also their relative amplitudes can tell you how the inclination of that star is relative to our line of sight because of cancellation effects of the different modes. And so in principle, at least, this allows us to measure inclinations of stars. And if we can then do that for host stars, we can get obliquities because we know transiting planets have to be inclinations of 90 degrees relative to the star. I'm saying in principle because in practice, it turns out to be very difficult to do. And even with Kepler, which is the best type of data we have for this purpose, we've really only been able to do it for a handful of systems to do it quite well. And so the overview picture of this is this somewhat confusing plot that kind of summarizes everything we've learned there so far. And it's not as much as you would have hoped for, perhaps. So anything that's low on this plot here at the bottom of the plot is aligned systems. So kind of like our solar system. Anything that's higher up here is planets that are misaligned. And if they're very high up here, they're retrograde. And so you can see there's quite a few misaligned systems, not nearly all of them, but quite a few are misaligned. That comes mostly from these Rossiter measurements for giant planets. But then in color are the ones that we have done in green with astrocosmology, and all of the other colored ones are also multi-planet systems. So that's kind of the systems we're most interested in. And so it's intriguing to start seeing a pattern where the ones we're doing with astrocosmology, the kind of smaller planets and so on, the multis, are mostly here, but then Kepler 56 seems to be an exception, and it's very small numbers, and so it's hard to know if that pattern would really hold. But unfortunately, this is sort of the summary of everything we've done with Kepler. We've really only had these handful of data points. There's been some ensemble studies and some other statistical things, but it's been just very hard to get this done very precisely. And so with tests, we won't really make a lot of progress there because test baselines are not really long enough. But hopefully with Plato, we will really be able to make some real progress on this type of question. And so that's one thing we're definitely looking forward to with the Plato mission, to make sense of this obliquity picture, which is a very much an open question in exoplanet science. We haven't really made all that much progress on. And so to come back to my picture, we first learned about eccentricities. And then when it comes to alignments, again, giant planets are regularly misaligned. For small planets, that may or may not be the case, and we just don't really know with current data. Okay, so with that, I want to leave the dynamics a little bit and move on to a few other questions that I want to briefly address today. First of all, I want to raise a question that has been on the mind of many exoplanet science, which is, do planets orbit all kinds of stars? And when you say all kinds, there's, I think, really two dimensions to look at. One is time and one is mass. So it's really a question of evolution or formation. With time, you can imagine planets might disappear, they might be tidally destroyed, and so on as stars evolve to subgiants, red giants, and white dwarfs. And with stellar mass, you're asking a question about formation. If you have low mass stars or high mass stars, do you still form as many planets or not? And there's quite a bit of theoretical work on both of these questions, which are both very interesting. There are predictions that formation does really matter. For example, because your lifetime of your disk will be different for different types of masses, because you have different amounts of material available, and so on. And as well for evolution, there's been quite some work suggesting that tides may really become important and may destroy lots of planets once stars start growing in size and evolving off the main sequence. And so the answer here is largely, again, open. It's been very hard to study this type of question. Again, the best data we have in terms of occurrences and demographics comes from Kepler, which was heavily focused on main sequence stars similar to the sun, for reasons of that those were the stars where we're hoping to find Earth analog planets. But over time, we've started diversifying the type of host stars we've been looking at. A lot of that has been driven originally by the K2 mission, different fields of the sky, but also importantly, community-driven. And so lots of people have started proposing to look at non-sun-like stars and actually looking at evolved stars and so on. And a lot of that actually driven by the stellar community. For example, a very big part of K2 was a Galactic Archaeology program looking at red giant stars. And so because this data is all open, it doesn't matter what the original purpose was of gathering the data. It can then be used to search for exoplanets as well. And so with K2, we've started really looking at different types of stars and really started trying to understand how, what happens to planet formation across the main sequence. And I just want to highlight a discovery that we worked on. This was from K2, which was K239. And so here you're seeing same major axes. So this is all close-in planets for different radius of stars. And so you can see here, this big blob here is really all the planets we know around stars, very similar to our sun. And so you can see the vast majority is there. And there's very few data points at all around these more evolved subgiant stars. And it gets harder and harder to go to the right of this plot. So there's some detection bias here, but it's also an intrinsic point that has been borne out now quite a few times. There are probably fewer planets around these more evolved stars, at least at short periods, suggesting that perhaps some of these planets do get indeed destroyed around these more evolved stars. But then again, K239 that we found here actually is at a very short period. It was the closest in planet around such an evolved star, and it hasn't been destroyed. And so if these tides are indeed so important, then because tides is such a strong function of orbital period, you would expect this system to start decaying. You would expect its orbit to shrink relatively fast, actually at the rate of seconds per year. And seconds per year doesn't sound very much, but it does actually come to what we can potentially measure. I mean, this was detected by K2. We're several years later now. And so retargeting these type of systems would start telling us whether indeed orbits are shrinking and whether indeed we can directly detect the influence of tides for some of these planets. And then K2 also allowed us to, for example, look at even other types of stars like white dwarfs here. This is a study I did with a student when I was in Leiden, where we looked at white dwarfs that were targeted by K2. And again, they were mostly targeted for stellar purposes, for people looking actually at oscillations around white dwarfs primarily. And so we used that sample and we looked for planets. At the time, there were none. Meanwhile, there's one planet detected with TESS on a white dwarf. But even so, with that sample of a few thousand systems, we could actually derive occurrence rates. We could try to understand how many planets could there be maximally to not see any. And so this is the kind of occurrence rates for different sizes and different periods. Not all these limits are equally strong, but it's interesting to see because white dwarfs are so small that you can actually hope to find really tiny planets on these. And so we actually have constraints on planets as small as Mars or Mercury because white dwarfs are so tiny. It's actually easier to find small planets there. And so planets are very likely quite rare around white dwarfs. But if there are any, they'll be excellent places to study because the white dwarfs are so tiny that you can do much more detailed studies. And of course, it's really kind of a bit of a golden era there in this type of research now because the TESS survey, which started in 2018, is an all-sky mission where we're getting photometry from the whole sky. And because we're getting photometry from the whole sky, we're also getting all types of stars, evolved, unevolved, and of very different masses. And so there's been a slow trickle of new discoveries, planets in clusters, planets on very young stars, and so on and so forth with TESS. And I think in the next few years, we'll really start understanding this type of picture in much greater detail than we do today. But I would like to move on to the final part of my presentation today, and that is going to be about the close-in planets. And so I want to remind you of this diagram I showed you at the beginning of the presentation, where I showed you that all these exoplanets really span a wide diversity of properties. And I want to point out that the transiting planets, the ones we've mostly talked about and the ones we know the most about, are really primarily interior to the orbit of Mercury. So essentially, all of these planets don't have an analog in our solar system. And so that's easy to forget. But it also means that these planets are likely quite different in some ways. And one important difference that had been alluded to, in fact, predicted back in 2013 by different groups of theorists, was that many of these close-in planets would lose their atmosphere due to photo evaporation. So what would happen is these planets receive a lot of starlight, and as a result, some of these atmospheres would effectively boil off these planets. Not all of them, but many of them would lose their atmospheres, and they would become what we would call stripped cores of planets. They would just be the planet core with no atmosphere left whatsoever. So that was a prediction that was made back in 2013 that should apply to essentially all of these planets, at least to the small planets in this regime. And so if you look at a cartoon image of sort of what these models predicted, they said, if you go to about 100 days and you look at the planets Earth to Neptune size roughly, you would expect many of these would lose their entire atmosphere. And so you would end up with 3 possible categories of planets. Let's say those that have a thick atmosphere, where the atmosphere actually is about as big as the core itself, but very low mass, mostly hydrogen and helium. And so not unlike Jupiter, but in a smaller version. And so you have these type of planets. You would also have some that have lost their entire atmosphere. So they would be the stripped cores, where they'll be only half as big because they've lost their entire atmosphere. And then in between, you have this category of sort of the thin atmosphere, maybe a bit like Earth. But they said it's very difficult for these planets that are so strongly irradiated to ever hold on to a thin atmosphere, which is very hard to hold on to when you have a lot of radiation. And so they said, well, you actually only end up with category 1 and category 3, not category 2 at all. And as a result, they predicted the distribution of planets should look something like this. There should be these planets here with a thick atmosphere, and then there should be significantly smaller, the planets that are stripped, that have only a core. And in between, there would actually be this absence of planets entirely. There would be essentially no planets there whatsoever. And so you can tune this and tweak this a little bit. You can actually move this region to different places. Where exactly this valley of planets would be depends on the kind of planet you think you form. If you form rocky planets, it's roughly where I'm showing it now. If instead you form icy planets, you would have it'd be harder to hold on to atmospheres. So more of these upper planets would end up below. There's more stripping going on. So your valley would move upwards. But the idea is always the same. no matter how you turn it, for specific samples of planets, you would end up with two categories. You would end up with a lack of planets around, for example, 2 Earth radii, and you would end up with this kind of valley, which itself depends on orbital period. If you go further out, radiation is less important, and so the valley becomes lower and lower because you're not stripping as many atmospheres away as you are at short periods. So this was this prediction, and this was made by several groups of theorists, which all essentially worked independently to come up with the same belief, saying this is what we must be seeing for these close-in small planets. And so, of course, with Kepler, we had lots of close-in small planets, and so we looked, and the early picture looked something like this. And so this was rather disappointing because there's really no evidence here of a valley or of really any structure in this original Kepler data whatsoever. There's really no structure there. You cannot see this confirmation. And so it's tempting to conclude that the theorists here kind of had it wrong, which wouldn't be the first time, of course, but in this case, at least, this was a prediction that actually turned out to be correct. It's just that us observers had to step up our game. Because what was really happening here is that we didn't know the size of these planets very well, largely because we were limited by how well we knew the stars, not how well we could measure the transits. And that's because, of course, we're measuring a relative size, we're measuring a transit, we're measuring the ratio of size of a planet to size of a star. And so as a result, the lower limit of how well you know a planet is how well you know the size of the star. In the early Kepler days, that uncertainty was about 25% on stellar radius and therefore on planet radius. And that meant that a planet that was really like this actually could be observed to be 25% larger or smaller because of the high uncertainties on the star. And so that would be this type of difference visually. And so it's really quite a big difference. That has gotten better over time with efforts, in particular Gaia, of course, has come along, but also with taking lots of high resolution spectra for many of these host stars and kind of shrinking uncertainties to typically now below about 10%. And that's a lot better. And I'll come back to these results in a moment. But I just want to say that with astrocosmology, and again, sort of like oscillators, specific samples of stars, you can do this type of work to 2% or so for if you pick the right samples. And that's where you can really start then learning in detail about the structure. And so what that means is that this original, rather disappointing looking plot with Gaia and with spectroscopy started looking like this. And so now here you can start seeing a hint of a valley at around 2 Earth radii, where there's a bit of an underdensity here of planets with kind of 2 blobs here below and above. And this was starting to look a bit more like the predictions. And this is about 1,000 systems, but then invoking astrocosmology for a subset of those, about 100, we could even shrink those uncertainties further down, and then things looked like this. These are astrocosmology data points. And so now you can really see kind of the two distributions with this kind of gap here in between, kind of exactly like what had been predicted. And so if we just show astrocosmology up here, this is how it would look like. And so we fitted for that valley. We used support vector machines to do so. And so we found that was located right there, quite rightly where it was been predicted, with indeed having this slope as a function of orbital periods and indeed being quite empty. And so we can compare two predictions. This is where predictions said it would be for different types of planets. Again, I said rocky planets would have been here. Icy planets, because they cannot hold on to atmospheres as much, would have this different location and having these different slopes. And this is what we observed. So again, kind of matching the slope, at least more or less, and matching the idea that most of these planets would be rather rocky. And then the fact that it looks rather empty suggests that most of these planets are having the same core composition, because if you invoke multiple types of planets, you start smearing out that valley. And so excitingly, kind of what we found here is that indeed this prediction from back in 2013, when there was no observations whatsoever to back up that prediction, actually turned out to be correct. And indeed, these small planets seem to come in two populations, where some have lost their entire atmosphere, their stripped cores, and some have held on to a thick hydrogen-helium atmosphere. Now, if all of that's true, then there's one more thing you can really test for here, which is to try to understand the composition of these planets. Because in particular, you would expect that those that have held on to a hydrogen-helium atmosphere have a much lower density of that planet, because that hydrogen helium takes up a lot of space, but it's very low mass. Whereas the stripped cores that are just just rocks in space should have a much higher density. And so the final point I want to make today is I want to have a look at compositions. And so this is just an image of the mass radius diagram of a subset of planets for small planets here, how it looked like a few years ago. And so as you can see here, it's a little bit of a mess. So this is the radii of planets. This comes the radius typically comes from the transit here, and to get the mass, you need the RV to complement that. So the RV is, of course, movement of stars, and so they give you masses of the planets. And then here, there's different models for different types of planets. For example, kind of rocky planets. This would be a 100% water planet, which isn't very physical, but it's just for illustration purposes. But the main point here, if you see this plot, is that this looks very much like a bit of a mess. It's not really easy to make any sense of this, and so there isn't really much that you can do here to interpret this plot. That said, it's an enormous amount of work to get these data points. So each and one of these data points requires tens of, sometimes hundreds of RV points. Each of these needs to be taken, is a spectrum that needs to be taken on a ground-based telescope somewhere over time. And so it's very painstaking work to get these measurements for all of these planets. But nevertheless, we haven't been able to interpret this very much. I've been involved in a team where I'm part of a steering committee called Gesprint, where we're doing a lot of this RV work and have been doing it for a few years now. In particular, following up TESS planets, TESS giving us brighter stars and more accessible planets for RV work. And we've gained, we really have been very successful at getting RV time, getting observing time at different telescopes, including now Espresso, new instrument at the VLT, as well as HARPS and HARPS North, and sometimes PHIS, CARMENES, PFS, and so on. And so we have published lots and lots of these type of new data points. Many have come from our group. And for example, currently we have a large program running on HARPS, which is about 95 nights. And we've just finished another large program with another 85 nights or so. So we have, I think, almost 200 nights on HARPS at the ESO 3.6 meter telescope in the last few years. So really huge amount of data. But of course, the question is, can we do something with it? Can we interpret it? And so as my final thing, I want to show you just one example of something where I think we have made some progress in interpreting it. This is a nearby M-dwarf star, so it's 22 parsecs away. It's one of the nearest planets, and it's a small star, so it's about 40% the size of the sun. It has 3 small planets, and so small really is small here, and one of them is actually Earth-size, true Earth size, at short periods. And so this is the 3 planets. This is TESS data. Here you see the different transits for the 3 different planets and the model of that. And so because this is so nearby, because this is 20 parsecs away, we can do more RV work than we could have in the past. In addition, we got data, RV data on the VLT, on the Espresso instrument at the VLT, kind of state-of-the-art, better than anything before, as well as some HARPS data. And so that meant we could measure the wobble of that star over time here. We followed it over a few months. And so you can see here, this is in gray. In the background is the model, is 3 different planets, and then all of them joined together, as well as some Gaussian process model is here in red, kind of mimicking indeed kind of what we're observing. And here are the residuals. And it's perhaps clearer if I show you this just facefold, so just taking out each individual planets. And so that's how things then look like. Here you see the TESS data with the transits for planet 1, 2, and 3. And here you see the same RV data for planet 1, 2, and 3. And so we can indeed very nicely here measure the transits on the left, which give us the sizes, and the RV signal on the right, which give us the masses. And so we can measure these masses here to quite good precision. And that puts us to an RV, a mass radius diagram that now looks something like this, where I'm only showing the ones where we have reasonably precise data points. And so this is the smallest of the planets where we've measured the RV point right here. So you can see it's fairly close to Earth and Venus here. And it's the smallest measurement we've actually been able to make in such a way. There's a few other data points here that are smaller, but they're all there's actually 7 of them. They're all TRAPPIST-1 planets. So this is the smallest that's not TRAPPIST-1, and then our other 2 planets are up here. The point here is I'm guiding your eye by color coding. Is in the bottom here, this gray color code is systems that all have a sort of rocky composition with no atmosphere. There's different types of rockiness. You can include more silicates or more iron, but they're all kind of rocky with no atmosphere, really. And that's what we think this planet's like. Then these 2 other planets are not consistent with that. And that means that either they have a very different composition. They will have to be very icy, for example. But it's very strange to think that 3 planets that are so close to one another, likely formed out of the same material, could have such a different core. But another alternative is that rather than having a different core, these 2 planets simply have an atmosphere of hydrogen-helium. And so this red model here is a model where this planet has the exact same core as the planet down here, but instead has some hydrogen-helium atmosphere on top. And so our interpretation is that this planet has lost its atmosphere of hydrogen-helium because it's the closest to the star and received the most radiation. These 2 planets were looking exactly the same, but held on to their hydrogen-helium, which makes them having a different mass, a different place in the mass radius diagram. And it's tempting to think this is the right interpretation because we linked this mass radius diagram to the radius valley. And this is now the radius valley for M-dwarf stars rather than for FG or K stars. And so here we're again seeing our planets. This is our planet, and these are our 2 other ones. And you're again seeing that indeed those planets that seem to be rocky with no atmosphere are indeed below the valley. And the planets that seem to be up here, that are consistent at least with having this hydrogen-helium atmosphere, are the ones that are also here above the valley. And so it's tempting to think that indeed there is this sort of lack of planets here, planets above have an atmosphere, planets below don't. That makes sense with predictions of photoevaporation in radius period space, but it also makes sense with the mass radius diagram, or at least it's starting to make some sense. So I will end here. I will stop here. So I touched on quite a few things, from dynamics, eccentricities, and obliquities to planets across the HR diagram, and the radius valley is interpretation in terms of period, radius, as well as mass. So I just want to say that it's a very exciting time in exoplanets still. We've answered lots of questions. It's been driven a lot by Kepler and K2, with now TESS coming along. And we're also still very much looking forward to Plato. I've alluded to it a few times. It will give us very precise transits, but also very good host star characterization. We're really hoping for some good astrocosmology, but also for Gaia, for example, to be further along with new data releases and so on. And so we're really hoping that we can answer quite a few more questions even with those future missions. So with that, thank you, and happy to take questions.
Thanks a lot, Vincent. Very, very interesting talk. I was going to say, theoreticians don't often get to gloat. So it's great that you, once in a while, observational astronomers can go back to them and sort of pat them on the back. So I can imagine, well, as you said, a lot was covered, but I would like to open the floor to questions. And similar to previous times, I'll take Joris' approach and sort of give priority to younger colleagues in terms of their academic level. So people can either raise their hand or post questions in the chat. So I see already a question by Matthias Fabri. So feel free to speak up. Yeah.
Hi. Yeah, it's a very cool results. I have a question on the eccentricity distribution of these planets that you find. Do you have this in function of period or distance to the star instead of as a function of mass?
So as a function of period, I was plotting here as a function of mass and not as a function of period. And period is the most kind of natural thing to do. But actually doesn't show very much. So what it does, it shows one thing, which is if you go to very short periods, a few days, then everything's circular, essentially, as you would expect from tides. But then once you go beyond that, at periods of about 5 days, you typically don't really see any period dependence at all. And that's likely because tides are a very strong function of semi-major axes. So once you go a little bit too far away, and you see the same in binary stars, I think. Once you go a bit too far away, then tides become entirely unimportant in shaping the diagram. And so as a result, as a function of period, it doesn't actually show you all that much. There's probably some interesting things to tease out as to, for example, how does it depend on the type of star? But we don't have that many data points to slice it up in these kind of categories. So we did look for some other correlations with period, with stellar type, and so on. And we haven't really found any, but I think it's probably the data quality that's been the limiting factor there.
And what about multiplicity? I mean, there's probably some general stability arguments that if you have multiple close by planets, I mean, if they cross orbits, etc., it would be a whole mess, right?
Yeah. So people have argued that in part, you could derive. So you would expect a multiplicity difference from the first principle that you need basic stability. So if you find highly eccentric single planet systems, you simply cannot put more planets in that system, or if you did, you wouldn't have the eccentric orbit, or things would no longer be stable.
Yeah.
And so people have tried that. There is also some people who've tried to come up with even kind of multiplicity eccentricity relationships directly, suggesting that, for example, the solar system is on the one end of the spectrum, having quite a few planets there, and you just can't make things all that more eccentric. We haven't really done that in our work. And again, the limiting factor is often that observationally, we don't know that very well. So even if we find a system that has 3 transiting planets, that doesn't mean it can't have 3 more or 5 more non-transiting planets or planets at longer periods. And so any relationship we're building is often, unfortunately, one where we're linking how many planets we see to something intrinsic rather than how many planets there are. And so it's not that helpful, unfortunately.
Yep. Okay. Thanks.
Yep. Thanks for your question. Next, we have David Petit.
Thank you. Is the mechanism for the valley or the absence of exoplanets in that radius mass figure that you showed purely the spectral or the radiance of its nearby host star?
So wait, so let me try to clarify your question. Are you asking what is the mechanism here that shows this value?
Yeah, like I'm curious if you happen to have some very, very, very calm star stellar remnant that's really not luminous or blasting any kind of radiative transfer onto the surface of the planet. Would this gap then get collapsed because it's being caused by such strong radiative transfer going through its atmosphere?
Yeah, it's a very interesting question. So again, on the data side, we're limited a bit by how much points we have. But so the basic mechanism, the basic predictions here come from this being related to mostly the amount of X-ray and UV radiation that your planet will receive. And so once you pass a certain threshold, you'll fairly quickly start boiling off most of your atmosphere, and you end up without anything left. And it's a very unstable effect. Once you start boiling off a little bit of atmosphere, you'll quickly start boiling off more and more. And so that relates primarily, at least in most of these theories, to X-ray and UV flux. And therefore, we also think it's likely that it happens fairly early, because most stars would have a higher level of XUV flux in the early stages of formation before they quiet down. And so if that's true, then you would expect that most of this happens early on, kind of earlier than what we're observing. And so it'd be hard to kind of tease out anything later. Now, all of that said, there is some alternative theories that have now been put forward to understand the radius valley that might have to do with also internal heat of your planet and how that would come into what you're seeing with different stellar types having a different dependence. So it's very likely, for example, that here you're seeing this is all essentially for the same type of stars. If you take different types of stars, you'd probably at the very least relocate your valley a little bit, and so that would then smear things out somewhat. And also, there's been now people who've, and this is the plot we made back in 2018. There's a few people who've claimed there is at least some planets kind of in the middle of this valley, which if everything was completely homogeneous, there shouldn't exist any planets there. But there seem to be some. I'm personally a bit skeptical of some of these measurements because, again, uncertainties and so on. But it's likely the picture is significantly more complicated and than what's shown here. And so there is very likely the case that, for example, if you looked at younger stars, you wouldn't see such a clear valley because it wouldn't have happened yet. But younger probably means less than 10 or 100 million years old. And unfortunately, we don't really know a lot of planets that are detected that early on. If this was an effect that really happened across the main sequence between 1 and 10 gigayears, we could probably trace it out. And in fact, some people have claimed there are some indications that there is still some effect ongoing even throughout the main sequence. But that's very, very difficult to do. It's also very difficult to get evolutionary stage or ages of stars right. And so, again, mostly these questions are kind of speculative at this point, certainly from an observational side.
Thank you.
Thanks, David. Yeah, Robin Byans.
Yeah, hi. Thanks for a very interesting presentation. I was wondering about the last system that you showed, where you said it's tempting to link the differences in densities to the radius valley. Are there any? Well, it sounds to me like it's a very a good explanation, but are there any reasons that it might not be the case, that it's linked to this radius valley interpretation of stripped atmosphere?
Yeah, so I'm saying it's tempting because the fundamental issue from a data perspective is if you make a mass radius diagram like here, it's degenerate. There's multiple possible interpretations for one single planet. So you can see these two data points are up here. I've indicated here this blue line here. That's kind of a pure water type of model. Now that's not physical. There's no way these planets are just pure water. But it just shows you that you can interpret the same. Here that red region is a region where you have a rocky core with some hydrogen helium. But alternatively, you can interpret it as pure water. Now we won't do that, but it shows you that it's very there's always multiple options. Here, for many of these planets, you could change their composition as well as their hydrogen helium content and come up with the exact same mass radius result. There's lots of degeneracies there. So just from the data, you cannot really go to the point where you can say, I know what the composition of these planets is, because there's multiple possible compositions. It's a bit better for the high density ones, because there's not so many degeneracies. If something's very high density, you can't really make it in many different ways. You kind of only need high density materials, and there's not many alternatives. For low density, you can make lots of different versions of your planet. So you need at least some additional piece of information to do this. And so the additional piece of information we are using to interpret things here for at least our system is that these three planets have periods of 3, 6, and 11 days. And so it's very likely they formed in the same part of the disk. If you're willing to believe that, then it's very difficult to say one has to be rocky and one has to be very icy, because icy planets would have to form much further out. And so if you do multi-planet systems and you're willing to assume that they probably formed kind of close to each other, then the interpretation that we're making here is very, very likely. But if you're not willing to believe that, or most of these data points are single planet systems, then lots of these ones probably are uncontroversially rocky. But the ones up here, you could well argue they're icy planets, for example, that formed further out. They might have been forming beyond the ice line and migrated inwards. And so that's not unreasonable to assume from just the mass radius diagram. If we link it here to the radius valley, as we're seeing here, then that becomes a much stronger argument that it's indeed related to the radius valley and to the same mechanism. And that's why we made this plot here for the first time. But we put this out just a few weeks ago, and so it's we'll see how whether everyone believes it. In defense of if you're more skeptical, this radius valley here, although it looks kind of convincing, is not nearly as clear as the one I showed you earlier, as the one I showed you here. There's just not nearly as many good data points. There's much higher uncertainties on these individual points, and there's much more reason to be skeptical, just because it's much harder to do for these type of stars. So it's still somewhat unclear. Mass radius interpretation has gone on for many years now. I think this is one of the first times we were able to sort of, I think, convincingly, I think this is quite convincing that this is indeed related and not just random. But it's probably a part of the story. There are certainly going to be icy planets that have migrated from further out as well, and so it's probably going to be contaminated at least by other mechanisms as well. And so it's not easy to do this. Each of these data points takes a huge amount of work. This one here was now very nice. It came out very nice here, but this was I think we took 5 or 6 nights on the Very Large Telescope, plus over 100 data points HARPS. So this is a very expensive type of data to do for just one system, at least with 3 planets here.
Right. Yeah. Thanks. I also think it's very convincing. It's nice.
Thank you.
Thanks, Robin. Okay, so I don't see any more raised hands. You can also use the chat, but we're reaching the hour. So if there are no more questions, I'd like to thank Vincent again for a very interesting talk. So the